Thank you so much for coming. I'm going to talk about deep learning workflow, more specifically, a couple of toolkits that I have been working on lately. So all of this happens because of the frustration that I've had from a couple of years working in deep learning. So before jumping in, I just wanted to understand the audience. How many of you guys are using Python? Can you raise a hand? Would be awesome. OK, awesome. Thank you so much. How many of you guys have done something related to machine learning / deep learning / AI? OK. Cool. So the toolkits that I've been talking about is Hangar, PyTorch, and RedisAI. So one last question. How many of you have heard about or used PyTorch? TensorFlow? More hands? OK, awesome. So let's jump in. So this is me. So you could find me from my tagline, second. I work at TensorWork. So TensorWork is a company collaborating with Redis Labs to build Hangar and RedisAI. Then I created TuringNetwork.ai. It's a deep learning exploration plus a deep learning exploration toolkit that helps you understand how your model is being built. So this is the workflow that I've been talking about. So it's a very naive picture, but this should give you the understanding. So we'll start from the ideation and planning phase, right? This is where you're going to get a client requirement or an idea that came to your mind about building a deep learning model. So you have an idea, you are planning, you're brainstorming through it, and once you have a concrete understanding about what you want to do, you move to the design and experimentation phase. So this is the phase where you decide which algorithm to use. Do you want to use, for example, an SVM for classification, or do you really need a neural network? How much data you need, et cetera, and et cetera. So once that experimentation phase is over, you sort of have an understanding about what you want to build, like a concrete understanding. Then you move to the model implementation phase. So model implementation phase, I'm going to specifically talk about deep learning here rather than other things under data science umbrella. So model implementation phase, you have an idea to build a neural network. So you're going to take that idea and build a network in some framework that you're comfortable with. You probably change the hyperparameters, change the architecture, change the layers, et cetera, and et cetera. And end of this phase, you will have a model built. Then you move to the training and validation phase. This is a phase where you need a lot of data. You loop through your data, you train your model, and almost all the popular deep learning frameworks available right now supports training and validation in the core itself. So you train your model, and you let the model learn from your data distribution. Then you validate that trained model with another set of data. So once you have validated the model's accuracy, then you're ready to ship it to production. So in this workflow, the two specific things that I'm going to focusing on is shipping to production and the central layer that runs parallelly through the whole workflow that you have, which has a couple of components like data collection, unit testing, et cetera. But I'm going to take this one thing called data collection or data curation, and how or why we built some tools that is going to help us to do the data curation. So I'm going to really quickly skim through the workflow and the tools that we use. So ideation and planning phase, you use things like, Google Doc, Jira. I use Sublime Text, et cetera, and et cetera. Then you move to the next phase, which is, design and experimentation. So if you have data, you try to visualize the data and try to understand the distribution, or you probably use, if it's deep learning model, you probably use some framework like PyTorch or TensorFlow to do the experimentation. Then you move to model implementation, same toolkits. Then training and validation. Okay. Training and validation, same thing. Then this is where the problem starts, right? So you have toolkits available right now to deploy your model to production. Several toolkits like TF serving for TensorFlow models, MXNet, MMS, my MXNet model server for MXNet models, Tensor RT on GPU by NVIDIA, etc. and etc. But one thing is there's no standard, and none of these are cakewalk. You have to spend a lot of time. You have to understand how it works. You need enough skill set to deploy a model to production. And if you want to scale, you probably have to use something like Docker plus Kubernetes stuff. And all of this requires not just what you already know, probably more tools in your toolkit or more resources, human resources to take care of each of this. So again, the last phase, or the phase that runs parallelly. Like I said, I've taken this one data curation thing. So what do you do to data curation right now, or data storage right now? Is it broken, right? So the problems like version controlling, can you do version controlling? Can you do diff? Cannot download the whole 10 TB, right? So can you partial clone a partial part of the data? Can you do that? Not really. So that comes to the first session of our talk, which is Hangar. So Hangar is the version controlling system we have developed, or we are developing. It's in 0.1.1 version now. We are working really hard towards 0.2 with a lot of good features. It's available in /TensorWorks/HangarPy GitHub. You should go and check it out and probably give us a star if you like it. So Hangar is, again, the version controlling system. It's quite different from the existing toolkits. The way it is different is because it's working on tensors rather than binaries. I'll go through that when we reach there. So Hangar is trying to answer this very question. Why the open source ethos that we had for code? Think about a stage where you don't really have Git for your data, for development, and how the development world would have been, right? The open source collaboration doesn't exist. When I say Git, all the version controlling system that you have for development. So we don't have such a setup, such an infra for dataset curation yet. There's no specific toolkits that we use to collect or curate the open source dataset. Nothing exists. So Hangar is trying to answer this very question by becoming the Git for data. So 0.1.1 is available in PyPy. We are working towards 0.2. So this is what we had till now. How do you guys used to store the data if you have like a big data set or data set coming in real time? You probably zip it. So what I used to do is I put it into folders, zip, and tag it with the date that I have, and probably store it in S3. You could serialize the NumPy arrays and store it in the disk. You can use protocol buffers, maybe HDF5, SciDB, TileDB, all these examples, all these existing toolkits. Store the data. This is what we have used so far. What went wrong, right? One main problem is different formats. So you're going to have like images, audio files, MRI scan files, different formats. You won't probably able to generalize all those formats to a toolkits that could handle all of them efficiently. So what we did so far is converting it to binary and serialize it to binary and save the binary. And that definitely has its pitfalls. So you can't really do diff and merge. Like if a couple of people are trying to collect the data and there's no good way to diff through the data or manage the conflicts, etc. that Git enable us to do. Another thing would be data access. So for example, if you have a folder full of images, you zipped it, how would you access that data when you want to run through a neural network? And neural network is just math operations. It needs numbers. It doesn't need file formats, right? So how will you convert it? So all of this raises the question how efficient you can do data access with the existing implementations. Then, like I said, the laptop that you're gonna mostly working on does not have enough space to probably store the big data set that you have. You probably have to take a partial clone of the data set and work through it. None of the existing toolkits could do efficiently. You probably can chunk your zip and download only the chunk. Then you probably end up having a skewed data set that is basically a small sample of your population. Maybe it's skewed towards some classes. So you're going to have like such issues. Hangar is solving this problem I think the first point that I want to bring up is Hangar stores data as tensors. So it doesn't really care about what your data is, an audio file, it's an image file. Hangar allows you to convert that to NumPy arrays and store the NumPy arrays in indexes. And it's a content addressable storage, so Hangar always create a hash of the data that you have and save that in a metadata. So everything Hangar saves is saved in this metadata. So metadata is like the visiting card for your data. So the last point, or the second last point is partial cloning. So when you partial clone it, what Hangar really does is Hangar take the whole metadata, which is small in size. Then if you just need 50 MB, it'll clone the 50 MB of data. So now you have metadata about the whole data set that you have and a small small part of your data. So even if you add another 50 GB to your data set, that's okay. And if you push it to your cloud where the whole data set is, you don't really break your system because metadata knows what data you already had and manages all the things that is going to come in this workflow. Hangar, we are building plugins, so we don't really want people to reinvent the wheel. So if you have like a folder full of images, JPEG and PNG or whatever, like audio files, you can just do Hangar import the folder name, Hangar understand the file format, take the files and convert it in NumPy arrays and save it for you and version it. Similar to that, one feedback that we have got from users is, since we are saving data as NumPy arrays, how you can interact with this data, right? You can't really go and see what's in it. So Hangar introduce export command, so you can take one particular data sample, and say Hangar export. It will export that to the format, what was it before, and then you can interact with some application like image viewer or whatever. So you can do all the other operations that Git allows you, time travel through your commits, zero cost branching, extremely cheap merging, etc. and etc. So with that, we wind up the Hangar talk. So now the data set is safe. You have saved it in your version control system. Let's move to the second thing in your pipeline. So I chose PyTorch here. You doesn't necessarily have to do that. For those who doesn't know PyTorch yet, PyTorch is a dynamic graph framework that lets you build the graph on the fly, unlike other static graph-based framework. But now almost all the frameworks are running towards building a dynamic graph interface for building the neural network. So like it shows in the GIF image, so you execute one line, it'll build only one line, it'll build only whatever is required for that graph. Then as you run through your program in the Python interpreter, it's going to build the graph and let you create a graph dynamically. So the benefits of dynamic graph is basically you can have dynamic decisions inside your network. So if there is an if loop, or if you have like a for loop, depends on the length of the sequence or something, you can really do that with the native operations available in Python itself. Another important thing that you should know about PyTorch is the torch.nn module that give you the high-level APIs to build simple/complex neural network. So almost all the popular layers are available in torch.nn plus activation functions. So you don't really have to create your own custom layer unless it is extremely necessary. The third thing that you should know about PyTorch when you take it to production is TorchScript. TorchScript, I guess, is introduced in 1.0. So TorchScript lets you take your Python program to like a binary, which can be run in a highly optimized or highly efficient C/C++ runtime. So there are two ways to do making TorchScript. One is by tracing. So you have a graph. In this example, you have the foo function that takes x and y. X and y could be a tensor. Then you use torch.jit.trace API. You pass a sample example. So what PyTorch does is PyTorch take that sample example, run through your function or model, and while running through it, PyTorch records the operations, and those operations then will be converted to a graph representation which is super optimized. So the second approach is by using script function /script module. So you can inherit from torch.jit.script module and use the decorator torch.jit script method that lets you create let you convert that class to a TorchScript module. Right, so now we have Hangar, the dataset source, then the PyTorch, the design, experimentation, or training and validation, model implementation toolkit. Now, how will you connect this two, right? So PyTorch PyTorch gives you like dataset and data loader APIs. So dataset essentially has a magic function len and magic function get item. So data loader takes a data set and make sure and get the length from the dataset len, and with that len, it'll create the range and use the get item. It'll get the items from the dataset. So it doesn't really worry about what is your underlying data storage or data source as far as it has len and get item defined. So the example here, the repo is equal to repository. That's how you let Hangar knows that a folder is a repository. This is how you access Hangar from Python interpreter. You have a highly flexible CLI available already, but you need this to access the data. So you do a checkout, you select the dataset name, dataset, and then you pass that dataset to Hangar dataset. So the dataset has len and len defined already, so you can just do len of the dset to get the number of samples in the dataset. Then you can access the data inside the dataset with the key. Yeah, so that's how you connect Hangar and PyTorch. So something like this is going to build into Hangar core very soon, but as of now, we probably have to do something like this, but this is fairly easy. So now you have dataset, PyTorch, and you connected these two pieces together. So you need to take this model that you are training, that you have trained to production, right? So we are using RedisAI for this very purpose. And here the example that shows is how to convert a PyTorch TorchScript model to a form which can be imported into RedisAI. So there's a Python client available for RedisAI. Obviously, the name is RedisAI. So you import save model from RedisAI. So the example that I'm using here is an example available in Torch Vision, a model.resnet. So it's a ResNet 50 network with pre-trained is equal to true. So you get a trained network. You convert that to eval mode. Then on the second last line, you create a TorchScript by using scripting. Then that TorchScript model will be passed to save model. Save model function can accept PyTorch models, TensorFlow models, ONNX models, even scikit-learn models, because you can convert scikit-learn to ONNX format and then pass to save model, which will save the actually, save model converts your scikit-learn to ONNX format. You can just give the scikit-learn model to save model function, right? So that's done. Now we're going to just talk about the last part of the workflow, which is deploying it to production. So if you have done this already, we have different production strategies. Like I told, TF serving is one, MMS is one. But in this instance, for PyTorch, what do you have? You have Flask, or Django, or I don't know, like any web server that's available in Python. Write a wrapper around your Torch model, then you can ship it to production. But then who will handle the scale, right? You have to put the effort, resource, and handle the scale with some of the toolkits or orchestration tool that you have. You can server, but that requires more effort. So these are the production strategies. So RedisAI is trying to solve and standardize these problems that we have for deploying the models. And the one question that I face from a lot of people is, everyone knows Redis, it's a database, how RedisAI can run, or how Redis as a database can run a deep learning model. So RedisAI is a module that can be loaded into a Redis database. It's made Tensor data type available for Redis. So now you can store a Tensor inside Redis database, and it turns the Redis database into a runtime, and the runtime is built on top of PyTorch, TensorFlow, and ONNX runtime. PyTorch is from Facebook, TensorFlow is from Google, and ONNX runtime is from Microsoft. Right. So, like again, I said, these are the backends, and more on the way. TensorFlow Lite is something that we are working on right now, and XGBoost is something we are working on right now. So, apart from this, since MXNet, CNTK, Chainer, and all this framework has an ONNX exporter, using ONNX runtime, you can essentially run the models from all the frameworks. So, when I was using TensorFlow serving probably more than a year back, it was not easy. Like I took like 3 days to set it up, and more effort to handle the scale, the issues, etc. So setting up a Redis server is like 15 to 20 shell commands. You don't really need to know anything more than this, and probably a couple of configuration changes. And since Redis has cluster support, it can scale. Since Redis has Sentinel, it has high availability and failover. You can use the whole thing available in Redis Ecosystem to scale it up. So this is a typical pictorial representation of RedisAI. The big red block in the middle is the RedisAI, which can run on CPU or GPU. We are even building the TPU support so you don't have to worry about what backend you want to use. You can take PyTorch, TensorFlow, or ONNX model, put it into RedisAI. You can take Tensor, any Tensor. We are using DLPack in the backend, so every Tensor will be saved as DLPack. The advantage is basically you can convert or you can use different frameworks in the same workflow without being worried about how to convert Tensor from one framework to Tensor in another framework. So the one in the bottom is TorchScript. So apart from model, you can also define a script, which is built on top of PyTorch. But the idea is, so that one typical example that shown in the bottom is conclude the whole idea. So as you know, Redis is a key value store. You save the tensors in a key called in-key. Then you pass that in-key tensor to script. So script is essentially a subset of Python language itself, but running not in Python interpreter, running on C++ runtime. So the script, you're going to define a script as a text file. Then you can put that into RedisAI. RedisAI take your tensor input, run with the function that you have defined in your script, and then the output of the script will take that and run in PyTorch or ONNX or TensorFlow runtime. Then the output of that is again ran by using another script. If you have a post-processing operation defined, then the output is then saved to outkey. So you can essentially mix and match different frameworks, scripts, etc. in the same workflow in RedisAI itself. So as I said, you can use the whole Redis ecosystem. You can make your model and tensors persistence by using RDB or AOF. Tensors, models, scripts, and all are persistable. Then client libraries are available in all the different languages, so you don't really get stuck with one language if your stack is already, let's say your stack is built on Haskell, and you don't now have to introduce another language to your infrastructure just to use deep learning, because the client libraries are available for RedisAI. Replication is possible with cluster, and Sentinel makes it the high availability available for you. So the example the picture that shows there is a 1 master plus 3 slave setup. So the master goes down, but Redis Sentinel makes sure and the slave becomes master without you interfering with the process. Then all the modules in the ecosystem. So if you check out the Redis blog or the website, you could see a bunch of modules that's available, like time series, the Redis graph, Redis stream, Redis edge. So you can use basically everything and build a flawless workflow. So advantages, you probably already have gone through almost everything, but I'll just run through this. So the first one probably requires an example. Let's say you have a natural language processing, a chatbot. Okay, so what you usually do is you send a dialogue. Then what you're going to get back is another dialogue plus the context vector. So you have to transfer to and forth this context vectors because there's no way you could save it. But since you are in Redis, you can save this context vector to a key inside Redis itself. So you don't have to transfer this forth and back. So that saves cost, that saves time, and you just have to pass the dialog to the Redis AI, and the Redis AI knows where to check for the context vector. It takes your dialog, takes the context vector, run through a sequence model, then the output context vector will be saved back to Redis, then you get the dialog back. You can keep the stack short if you already have Redis inside your stack, which is highly likely. You can optimize the use of resource. You don't really need a lot of resource, human resource / infrastructure resource, like if you're using other production deployment toolkits. You can run everywhere Redis runs. You can run it on a Raspberry Pi. You can run it on a highly grade server. You can run it on your laptop. It doesn't matter. Like all the backends we have defined. You can stay language independent. You can use any language of your choice. Keeps the model hot. Sentinel for high availability, cluster for sharding, and all those stuff. Auto batching is something that we are working on. So for those who doesn't know auto batching, if you have 10,000 requests coming in a second or together, in a normal way, you would execute your model 10,000 times, which is highly inefficient. So with auto batching, RedisAI smartly collate all those 10,000 examples into different batches and execute it in a batch and return the response as it requires. Running async, that means the clients are not async now. Clients will block your, the RedisAI will block your client now, but we are working towards making it async. So I have 3 examples in 3 different languages. This is a Golang example for doing ResNet 8 classification. So if you check it out, you have a model set that sets the model, then a script set that sets the script, then a tensor set for setting the tensor. Then you do model run, script run, and get tensor get to get the tensor back. The same example is in NodeJS. And so it is doing the same thing. The first function is for loading the model, which saves the model into the RedisAI runtime, then running the model. The last example that I have is obviously Python. So the exactly the same thing, but a more user-friendly interface is available right now with RedisAI. So if you look at oh, no, it's not there. So basically the package that we are using is the default Python package for Redis. That's why you have to give the commands, but now there is a RedisAI client available where you can use client.tensorset instead of passing tensorset as a command, which is more user-friendly. Yeah, I think I'm done. Really welcome your feedbacks. Any feedbacks, we will try to push back to the development lifecycle. Contributions if you are interested, and yeah, of course, GitHub stars. Thank you so much.